Hello, everyone. Welcome to our first Pawsey Friday. I'm Aditi. This is our first online event from Pawsey as well, so please be forgiving if we have any hiccups along the way. We hope you enjoyed today's event about why quantum computing. So I would like to welcome Pawsey CTO, Ugo, and he will introduce today's event to you. Thanks, Ugo.
Yes, thank you very much, Aditi. Indeed, this is the first time we run an event like this, and it's quite interesting for me, right? It's the first time I speak in front of an audience I cannot see, so that's very interesting indeed. Let me begin by acknowledging the Wajik people of the Noongar Nation as the traditional owners of the land that we're meeting on today, and pay my respect to their elders, past and present. And I would also like to acknowledge that all the elders on the lands you're on today, since today we do have a diverse group of people from across the nation with us. Just gonna say a few words about the current activities going on at Pawsey before we start with the presentations. And the first one is related to the Capital Refresh program, which we started a few years ago at this point. So the status today is that our new cloud infrastructure is fully deployed and operational. The MWA cluster, it's also fully deployed and operational, and we are just finishing up testing it and addressing some minor issues related to the software stack. The other topic I was going to discuss is also our interest in quantum computing. So we are interested in both quantum computing and quantum computation, meaning that quantum computing for us means how to operate a quantum computer inside a supercomputing center. Because at some point we might have to hook up an actual quantum computer to the rest of the IT infrastructure we already own, right? And that's really how we started the conversation with Quantum Brilliance. It was really about understanding what it means to operate a quantum computer. So that's one aspect of it. The other aspect is the quantum computation part, meaning gaining some skills and knowledge about quantum computing to understand how to properly support our users going forward, and understanding what it will mean for the users to move towards such technology. So that's about it. I'm going to introduce now our first presenter, Professor Jingbo Wang. Professor Wang is the head of the physics department at the University of Western Australia and a pioneer of cutting-edge research involving single and multiple particle quantum walks. Professor Wang does lead an active research group looking at quantum simulation, quantum walks, and quantum algorithm development. And her research team was the first to show the power of quantum walks in extracting local and global structural information of complex networks and in distinguishing a range of non-isomorphic graph classes. Recent work from Professor Wang also includes quantum simulation of designer functional molecules and materials, exploring fundamental structures and symmetries in nature. So I will now let Professor Wang give her presentation, thanking her for joining us today. Please.
Thank you, Ugo, for the introduction. I'll start to share my screen. And okay, I assume you can all see. So thanks everyone to come along during such a rainy day. So today we are here to talk about quantum computation, which is a new paradigm in science and technology, which involves entirely new design architecture in comparison to our conventional computers in both software and hardware. And it holds the promise to solve problems otherwise intractable. I'll start to talk about where we were and where we are currently now and the future. So we have come a long, long way in the development of having computational tools to help us in the day-to-day mathematics computation. So it started many, many years ago. And I think Abacus, if you look at it closely, it's a computer. It records numbers, you can write and erase. And according to certain rules, you can obtain your computation results. And then we have the Pascal's mechanical calculator, which is a gearbox, up to the Babbage calculating machine, which is designed to achieve computation otherwise you cannot do by hand. So the real achievement was the first electronic computer, which was based on the vacuum tubes, and it played an essential role in World War II, and possibly helped in many ways to win the war. So that's a stack of vacuum tubes. For younger people, you may not have seen it. It was a real milestone set in the 1940s when this was come to full operation and clicking away day and night. There was an overwhelming pride in this achievement, such as, this statement was full of optimism, even though it looks a bit strange for now. It says, where this first electronic computer is equipped with 18,000 vacuum tubes and weighs 30 pounds. Computers in the future, it will be much better. Yeah, it may have only 1,000 tubes if we design it properly, and it will weigh only 1.5 tons. And we all know now how wrong that statement was, but it was stated. You can feel this overwhelming pride. And we have a machine which will be able to do things which may require, would have required thousands of people. What made the change is, of course, the new discoveries in physics. The first transistor was discovered, was invented in 1949, and which actually led to a Nobel Prize for 3 people, Brandon, Shotley, and Bardeen. So that started this very rapid development of computing device, and mostly due to the rapid shrinkage of electronic components. So in the first one is this integrated circuit in 1970 or 71, which has about 2,000 transistors. And now we have billions of them. And they are stacked in 3 dimensions. And it works everyone now. Everyone's life has been changed ever since. So this still continues on. And I'm showing here as a comparison, I'm actually showing a picture of the flu virus. So the flu virus is about 100 nanometers in size, but man-made structures is it's carried on to nowadays it's just 1 or 2 or 3 nanometers. But you possibly have noticed the size reduction has not really followed the Moore's law anymore. Started around 2006. I'll show you such a graph, which has a collection of data about the clock frequency or clock speed from Intel IBM, Sun, and others. And there's a clear plateau, flattening of the increase of speed, which corresponding to the reduction in its size. So if you bought a computer around 2009, 2006, and this is an iMac, which actually I have, it achieved 2.16 gigahertz. That's an Intel dual core CPU unit. If we follow the Moore's law, and by now, which is almost 14 years later, the prediction would be we would have an 800 gigahertz processor to use. But the reality, if you go to the shop to buy one of the best iMac, and the clock frequency, it hasn't really changed much at all. It has a few more core, but that's it. So if we want to keep the same kind of trend as we would have hoped, because the data around us has been doubling every year, faster than Moore's law. And if we want to keep it up, we have to think beyond the box. Currently on the table is this quantum processor, and it works on fundamentally different design principles. As I said, both hardware and software. And as William Phillips said, quantum computation is going to be a radical departure in information technology, more fundamentally different from current technology than the digital computer is from abacus. We all know how little abacus can do and how powerful our current computer is. So that revolution is expected if we move into the quantum domain. It all started by a few pioneering researchers, and such as Richard Feynman. Around late 80s, he started to ask questions, such as, let's think about what would happen if we consider bits written on one atom instead of the present 10 to the power of 11, and that's close to 1 trillion atoms. Such nonsense is very entertaining to professors like me. And then people start to think, what would it look like? For a long time, this was just a playground for pure theoretical physicists and for people really interested in quantum foundations. And let's say what would be like if we use a quantum particle to encode information rather than voltage or current, which involves 1 trillion possible photons of electrons. So let's see how we do it. I mean, a bit is really a 0 and 1. As long as we can distinguish one physical state from the other, we have a qubit. So if we use an atom as a qubit, and the ground state is 0, the excited state would be 1. If we use electron spin, if it's pointing upwards, the electron has 2 degree of freedom in the spin space. It's pointing upwards or downwards. If it's pointing upwards, it's 0, pointing downwards is 1. And you can use photons. Photons has polarization. If you polarize in one way, it's 0, and the other orthogonal way would be 1. What is different comes from a unique property of quantum particles. When I say unique, actually I meant entanglement. And many people say a lot about superposition, but superposition, actually, if you think about it, we have it in the classical world. We have superimposed water waves, sound waves, electromagnetic waves. And if you really can control it and play with the orthogonal modes, many of the other things I'm going to talk about, many of the quantum algorithms can actually be implemented to a certain degree. And I want to state clear and loud, the entanglement is something which is very unique. I will try to demonstrate both and say, hopefully, can demonstrate the power. So what are the superposition? So let's use quantum particles. And for example, an electron. And if it's a classical particle, you can have this particle here or there. If it's here, and it's 0, if it's there, you can see, yeah, it's clearly outside. They have their own domain, and that's 1. But a quantum particle can be here and there at the same time with certain probability. So that's the superposition. And if it can be in both positions and you have a quantum state, you can write it as both here and there. It's in a superposition. You may ask, so what? And the other thing which is very, very important and unique is this intrinsic quantum property called entanglement, where 2 particles or 2 qubits can be very, very far apart. However, if you do a measurement on one, and you will have immediate, instantaneous effect on the other. Okay, let's say what happens if we have 3 qubits, and if we set them up all in equal superposition of being 0 and 1, then you will have a superposition of 8 states all at the same time, starting from all 3 qubits pointing upwards to all 3 qubits pointing downwards, and everything in between. And if you think about a bit more, like 1,000 qubit, and this will encode information of 2 to the power of 1,000, which is equal to 10 to the power of 300, and that's bigger than the total number of particles in the whole universe. And if you can design a quantum process to manipulate and drive your quantum state based on all these numbers to compute some resultant function, and you're actually effectively doing 10 to the power of 300 computations all at the same time. And is that too good to be true? And the answer is actually yes. In a quantum system, there is another thing which is very different from the classical world we're very used to, and it's the measurement of a quantum state. In the classical world, it's simple. You look at it and you are not going to change it, and you take a note of its state and you can write it down. But it's problematic in the quantum world because measurement actually collapses the superposition into just one outcome. I'll give you an example. Let's say this is an imaginary quantum computer, and we give a very simple task of doing this logical manipulation. So the F value is dependent on some AND, complementary, and OR operation of A and B and C. So the quantum computer will use all possible values of A, B, and C. Let's just assume it's only a qubit, not qubits. So it has just 0 and 1. We would set up in the quantum computer such a quantum state. So if A, B, C is 0, and you can quickly check, classically you can check one after another, but quantum mechanically, you can do them all at the same time. So that will give you 0, and 0, 0, 1 will give you 0, and so on and so forth. So after the quantum logic manipulation, your quantum computer will be in an entangled state of the input register and the output register. All fine. Quantum computer knows everything. We don't. If we want to know anything, we have to measure it. We have to look. And if we do, this is what's going to happen. So let's just look at the output register. It can be 0, or it can be 1. But if you do a measurement, 3/4 of the time, you can calculate the probability. So 3/4 of the time, you will get a 0. And 1/4 of the time, you get a 1. So let's say your result is 1. This is what's happening. And the help space collapsed. So your wave function will only have 2 terms immediately, okay? And if you do another measurement, half of the time you will get this, and another half time you're getting that. And we say the Schrödinger's cat, before the measurement can be both alive and dead, and now it's either completely dead or alive. It can't be both. So quantum parallelism is not parallel computing. And in Pawsey Center, if you send a code, you do parallel computing, you have all the results. But here, you do all the computation, and towards the end, you just get one outcome. And you don't even know which one you are going to get. So why waste time and money? So here is the trick. And here is why it's very, very difficult to come up to design quantum softwares which will be able to provide useful answers. You have to be able to achieve this. You have to be able to manipulate all superimposed states, superimposed and entangled state at the same time, which you can do without looking. But you have to design your algorithm to work in such a way, when you do look, it gives the answer you are seeking for. If you can do that, the sky is the limit. I will use 2 examples to illustrate this. One is the it's best well-known Shor's algorithm. And the second is an algorithm devised by my research group.
Hey, Jingbo, just to let you know, we have 1 more minute left in the presentation.
Okay, so I'm rambling for too long. Okay, so what should I do? No?
5 minutes is fine, yeah.
Okay, I'll go
Thank you.
quickly. Yeah. So, so Shor's algorithm is to try to find the prime factors of a composite number. And number theory tells us we can do it in a different way. Instead of checking if the number is the factor of a composite number, you set up a function as such, and where this is the composite number, and this function will be periodic. The period will tell you what the factors are. So it converts the problem into finding the period of a function. And the function I'm plotting here, and this is a fairly simple function, therefore the period is quite small, and we can say by our eyes it's 4, but a quantum computer will do it this way. So after you set up this wave function, which is entangled, entangling the input and output in such a way, and you do a measurement. So the measurement, as I said before, it will collapse into a single possible value. So it can be any one of the 4. And suppose we collapse the function into this value, and magically all the other states disappeared. And as you can see, you are left with the state was perfectly separated by the period. And if you do a Fourier analysis, you get the R, and then you can calculate the factors. Okay, 3 minutes about my work. So actually, this is not really my work. So it's my PhD student, Sam Marsh. He's currently a third-year PhD student working in my group. So his task is trying to solve really, really hard, but practically very useful combinatorial optimization problem. I'm going to skip, just to show you how difficult they are. Anything, even traveling salesman's problem, if you want to visit 17 cities, it's already 10 trillion possibilities you have to calculate and have to compare. I use graph partition as an example. And as you can see, if I have a graph of 500 nodes, to find the best partition, which means the connection between the two groups is the minimum, will require 10 to the power of 150. So it's a very, very, very difficult computational task. Conceptually, it's not hard, but in reality, you can't compute it. Okay, so I don't have time and to go into the details. I just go through it fairly quickly. One very popular approach is called quantum annealing. What happens here is you encode your problem into a Hamiltonian where its ground state provides the solution, but it's very, very difficult to find. So you start the system with a well-known simple Hamiltonian where you know its ground state, and you start from the ground state and you change it very, very slowly. And by this adiabatic theorem, the system will stay in its ground state all the way through, and then towards the end, if you change your Hamiltonian to the problem Hamiltonian, you get the answer. The problem is when the system becomes big and when the system becomes complex, you often have the problem of the spectral gap, which can be very, very close to zero, exponentially small. And therefore, when you're coming across this point, if you don't drive the system slow enough, it will jump into another state and you end up with a very wrong answer. Okay, so I will just go to what we are going to do. We are going to employ quantum work, which steers the amplitude into the right solution. I'll show the animation and then I'll stop. Okay, so 2 steps into what we designed for. One is we have to be very clever to index all the possibilities and filter out unfeasible solutions. And therefore, we work in a much smaller help space. And second is we connect those solutions by circulant the graph. Why circulant? Because circulant matrix can be diagonalized by Fourier. And we all know the quantum Fourier transformation is exponentially fast. So we can prove this circuit is highly efficient. We only need log n factorial qubits and poly log n factorial gates. Finally, I can show you the results. And we start with, because we don't know which solution is the best, we start equally as an equal superposition. And then we have a phase. The phase gate encodes the quality of the solution, followed by a quantum work. I'll just show the animation and then I'll finish. Okay, you can see each node is phase shifted differently, and that difference tells us which solution is good and which solution is bad. And then we do the quantum work, which distribute which does the mixing. So the amplitude flows. If it's designed correctly, in a minute, will converge into the desirable solution. One more step. So at this point, you can do a measurement, and these two are equal best solutions. So we can measure them with high confidence. I don't have time, but we have come a long, long way from the Shor's algorithm and Grover's search algorithm. And now we know quantum mechanically, we can solve large set of linear and differential equations of certain fairly restricted classes. And we can find eigenvalues and eigenvectors of very large scale matrices, and so on and so forth.
Okay. Jingbo,
I'll finish.
Sorry to interrupt, but I was told that your time is up, and not keeping track of time myself, but apparently you have to finish your presentation as you can, please. Yes.
Yeah. So I'll just leave one question for you to ponder. Like in the 1940s, a lot of people said we were dreaming. The electronics people said there were too many vacuum tubes, it would never work. The mathematics people said there were no problem complex enough that computers were needed. And now we're asking a very similar question: is quantum computer still just a dream? And I'll leave this to Professor Hollenberg. Thank you. Sorry.
Thank you.
Yeah.
Yeah, sure. No problem. Thank you very much. Actually, I would have liked to see more of your work presented, but clearly we don't have time, right? Just going to make a couple of comments here, not really related to quantum per se, but in your presentation, you were talking about advances in technology, right? And until today, we have been linking advancement in technology to size, right? The smaller, the better, the faster. Now we have to think differently. Now it's really about using a different property of materials or matter to encode information. That's really a huge change in paradigm, right? So that's one comment I was going to make. And the other one is about the distinction between quantum parallelism and parallel computing. Because so that you know, when we started talking to quantum brilliance, right, one of my colleagues who is actually in the audience today, first thing he said is that he wanted to parallelize quantum algorithms, right? Or at least look at what it meant to parallelize quantum algorithms, right? And that's really exactly the point, because the way we work today is that we solve problems by parallelizing and getting exact answers, right, out of the parallelization. But that's a completely different way of thinking here, right? And that's the part that I believe we are not ready yet to face, right? That's the part where we need a lot of work, right? Also in terms of changing, the mindset, the way we think about things, that's it. That's what I was going to say. Great. So conscious of time, I'm going to go ahead and introduce our second presenter. Actually, I should have said our other presenter, but I don't like the first and second thing. But so Lloyd Hollenberg. Professor Lloyd Hollenberg is Deputy Director of the Center for Quantum Computation and Communication Technology, and an Australian Research Council Laureate Fellow. He is a well-known proponent of quantum science and technology in the wider context, having also worked on developing ultra-sensitive quantum sensing and imaging techniques, crossing over to the nanobiology realm. Now, please, Professor Hollenberg, if you want to go ahead with your presentation, we will be delighted to hear what you have to say.
Okay, thanks very much, Ugo. Can you hear me okay? All right, so thank you very much for the invitation, and hello, everyone. The weather over here in Melbourne is actually quite nice. It's becoming evening, but it was a nice sunny day. Jingbo gave a really great introduction to quantum computing and computation, and I'll build from that base and talk about what the state of the art is and where we go from here. And I'll focus on some of the connections with high performance computing. All right, so I'll start with just an overview of my group. So as Ugo said, I actually work in a number of areas in quantum science and technology. In quantum sensing, we have our lab that works in nitrogen vacancy centers in diamond, single qubits in the language of quantum information. And in quantum computing, we work pretty much all theoretical. with the caveat that a lot of the theory work is now being carried over to IBM Q systems. So for a theorist, that's getting close to doing experimental quantum computation. Within the Centre of Excellence for Quantum Computation and Communication Technology, I work on a particular physical platform, which is silicon quantum computing, where, as Jingbo said, we're trying to encode bits on single atoms and, in fact, the spins of electrons and nuclei. Okay, so let's go forward. So this has already been covered, the conventional introduction to why quantum is often couched in the language of Moore's law and how that's starting to plateau, as we just saw. But what I'll do is I'll try to look at the complexity diagram in the context of both classical and quantum, and you'll see the differences here. So this is a ridiculously simple picture of classical complexity, so don't hit me with NP and all the rest of it. I'm really trying to articulate that broadly there are relatively easy problems that we can solve classically, and then there are hard problems that scale exponentially and require exponentially more CPU resources to solve. How does quantum computing look compared to that? Well, as we saw, quantum computers are based on the laws of quantum mechanics, and via that we can start to circumvent some of the limitations of classical processing. But the information processing is very different. And so when we try to think of how the quantum complexity diagram looks compared to classical, this is one way to view it. And so within the quantum framework, we're starting to butt up against some of the hard problems. So Shor's algorithm is in principle exponential speed up compared to the best known classical algorithm, but not all quantum algorithms do that. And I'll be talking about Grover's search algorithm, which is a root n polynomial speed up, but even that can actually be significant. And so when I talk about quantum easy and easier, by quantum easy, I mean something that will provide an exponential speed up like Shor's algorithm. And then quantum easier is something that provides a polynomial speed up like Grover's algorithm. And currently what people are doing, I've just got to move things around a little bit. Okay. What people are trying to do now is expand that front of interaction with various problems in the quantum space. So in other words, developing quantum applications. And these are applications broadly in optimization, in finance, AI, and material science. And there's a longer list, but I'm not going to talk about all of those. Okay, so where are we now? So in 2016, IBM significantly provided cloud access to one of its devices. This was a 5-qubit superconducting device, and it was essentially put on the cloud for anybody to access through a programming interface. And we'll have a look at this in a little bit. And that was very significant because it allowed almost anyone who had a rudimentary knowledge of quantum computing to actually start programming and having a look at how an actual quantum computer works. It was a fairly limited machine, fairly noisy, but that's basically set the scene for gradual improvements, in fact, rapid improvements in not only the interface and the whole ecosystem of software around that, but also the hardware itself. And in 2017, to really accelerate the engagement with end users such as myself as a researcher and people in the corporate space, IBM launched the Network Q. And I'll talk about that a little bit as well, because at Melbourne, we've established one of the Network Q hubs for the Australian region. Of course, there are other platforms that are being developed, and you've heard about the Google system, I'd imagine. I'll say a few words about that. Companies like Rigetti and IonQ and Microsoft. There are lots of different systems out there, and D-Wave were amongst the first to develop a system that you could program, and that's under the adiabatic quantum computing framework that Jingbo was talking about. So state of the art for IBM are the System 1 machines, which comprise devices between 20 and 53 qubits with very good error rates. but they're not the only ones. Google, you would have probably noticed last year, announced their quantum supremacy result. And so this is entirely worthy of some comments here. So what is quantum supremacy? It's the point where a calculation done on a quantum computer can outdo a classical computer. Supremacy is probably not a great word. Quantum advantage is something that I prefer to think about, and I'll define that in a moment. But what was this all about? So it was a 53 qubit machine. The computational task that was set was to simulate a random quantum circuit. And you can see in the picture there that this device was basically a two-dimensional array of qubits with a whole bunch of gates. This is time going along in that direction. There's a certain structure to how the gates are defined, but at the end of the day, you would do a measurement over all the qubits. And for a random circuit, that probability distribution of the measurement outcomes is actually quite scrambled. Nevertheless, it's fully defined by that gate structure that you have in there, even though it's random in a sense. So the task is on a supercomputer to simulate this quantum system of all of these qubits, all 53 qubits, with a certain number of time steps with random gates in there. And then compare that with the same set of random gates on a quantum computer. Now, a quantum computer runs once and gets one value out for all of these measurements here for each qubit. So you have to run many times to sample from that distribution. So it's all about how accurately can you sample and how long does it take you to do that. And so the analysis showed that for the largest cases that the quantum computer could handle, it was taking about 200 seconds to do all of that sampling and to demonstrate correct sampling from that probability distribution, versus what would have taken on the Summit supercomputer they were using some 10,000 years. So that's all in the Nature paper there. It's a wonderful paper. IBM has counted to a certain extent on the details of how you use that particular computer, because it's one of theirs. And they were saying it's more like 2.5 days on that machine if you take data processing and all of that into account. For me, it's not so much about the 10,000 years versus 2.5 days. For me, the big thing about this is if you are arguing about days on one of the largest computers in the world, then what this has demonstrated is that there is non-trivial quantum information processing happening in this device over 53 qubits, which, as we saw from Jingbo's talk, is representing to the 53 states. And that, to me, is really clear evidence for large-scale quantum information processing. But as I said, the big goal is not so much this idea that on a toy system like this, where the quantum computer is simulating itself, that you can beat a classical computer. It's whether you can derive advantage from a quantum computer, and that's quantum advantage. And the question there is, can it happen? And if so, when? And what do you require? So just to complete the story on the IBM Q network, to me, this is really the state of the art in terms of not only the hardware, the hardware is going to sort of go toing and froing between the major companies, but the IBM Q network is really the state of the art in terms of engagement with the wider community. And you can see now it represents a lot of organizations, a number of hubs such as ours at Melbourne, corporate members, startups, academic members, and industry partners. So it's a very large scale effort now all across the world. And in Melbourne, we've established an agreement with IBM that allows us to access not only the IBM Q network and be a part of all that, but also the premium level devices that are offered through our cloud access. Okay, so let me talk about practical quantum computing, because I think that's what people wanted to hear. So to begin that journey, I just want to take people through the system that we developed at Melbourne University, which was to allow in teaching and research contexts the students and researchers to really unpick what's happening in a quantum computer. So this is some copy here that I was very proud of. A quantum computer is the ultimate black box. And what I mean there is if you have an actual quantum computer device and you run a quantum algorithm, all you can really do is measure at the end. Yes, you can do a bunch of measurements in the middle, but if you do so, you'll collapse what's happening and you're not going to get a really good picture of what's actually happening within that device during that quantum algorithm. So it's systems like this, which are theoretical, that allows you to really go through a quantum algorithm step by step and really unpick what's happening there. And that's really useful in teaching. We use this system now to underpin our teaching. You can just access it at qespace.org and register, and you can play around with it yourself. Our students use it in all their lab classes, and we have a master's subject and an undergraduate subject that's dependent on this. For us, it's going to be a way to visualize what's happening in these quantum algorithms. As Jingbo covered, the way a quantum algorithm works is not so much doing a whole bunch of calculations in parallel. That can be part of it. But really what a quantum computer does is use all the subtle interference and entanglement effects in quantum mechanics to amplify probabilities, and specifically to amplify the probability of your answer, so that when you measure your quantum computer at the end, you have a higher probability of measuring a particular state, which is in fact the answer. So I like to draw a bubble representing a quantum superposition. A quantum program is basically evolving in time, probability peaks or amplitudes in a quantum sense of all the different strings or values in a particular register. So that at the end of the day, there might be one particular string that's amplified in probability over all the rest. And when you do a measurement, you burst that bubble because it collapses the state, but will, with a high probability, burst it into the state that you're actually after. And that would be the most probable result. Okay, so how do we see this in practice? So a good way to see it is through what's called the quantum search algorithm. So that's Grover's algorithm. So here is the QE system programmed to run one iteration of Grover's search. And I'll just take you through that. So if you can see, we've got 3 lines corresponding to 3 qubits moving from left to right in time. And each of them have been initialized in the state 0. The first line of gates, these are so-called Hadamard gates, puts it into a superposition state where every binary number is represented in a superposition. And Jingbo showed us how to do that with 3 qubits. So effectively representing binary numbers from 0 to 7 in superposition. But of course, that's useless. You can't do anything with that because if you measure, you just collapse at random and you'll pick just one of those states. The trick is to mark a particular state. So let's set up the problem with an oracle that marks a particular state within that superposition. Of course, it's a very artificial problem that tells you very effectively what's happening. So the oracle here is designed to mark a particular state, the number 5, so in binary 101. And you can see that we've put our slider here, and that's now giving us the output corresponding to the state at that point. And you can see that these are all the amplitudes. This is 0, 0, 0, all the way up to 1, 1, 1. And the blue just represents the fact that there's 0 complex phase associated with their numbers. They're real numbers and they're all the same. But here for the mark state, what this little snippet does is put a minus sign in front of that amplitude. That's totally non-classical. You can't do that with a classical register. So that marks that state as being different. And then when we push the system through the inversion step, that's basically a way of calculating an average of all the amplitudes and then subtracting that away from each one. And when you do that, you'll get a different result for the state that's been marked. So once it goes through this inversion, we now see the probability for the state that we marked is much, much higher than the rest. And that means that when we come to measure, we have actually picked out the state 101. In other words, this is a very real example of how those quantum interferences work in a quantum computer.
Lloyd, you have 3 minutes left.
Yep. Oh, okay. So does that mean I have another 5?
I
Okay,
think we
so
can go with 5.
Okay, like Jingbo, I've gone a bit slower than I thought. So let me show how this works on an IBM Q system. So you can literally drop and drag gates in the same way as you do on the QE. So you see a very similar circuit there. You can pick a particular back-end device, and this is one of the public devices. This circuit now is compiled for the hardware. So not every gate here can be done on the hardware. And then, for good measure, you would first simulate using their simulator or emulator if you add in all the physical properties of gates. And that can handle up to 32 qubits. And you see that you get the same results as the QE. Now you run it on the actual back end. And here you see the results. So this is running on an actual quantum computer, this 3-qubit problem. And you see it picks out the signal for the correct state. But you can see now that the other states now have a higher probability that things have been adjusted. And this is due to errors, logic errors in this device, which, because it's one of the open devices, are a little bit noisier than the premium devices. So where does HPC come into it? So we developed a capability to simulate very large-scale instances of quantum algorithms. And this is an example done by one of my students, Aidan Dang, who virtually in this one calculation went through our whole allocation on the Pawsey machine. But that's okay, we were pretty confident that it would finish. And this was essentially simulating Shor's algorithm, which requires for an L-bit semi-prime number, 3 L qubits, which means the space of complex amplitudes that you would have to store on your classical device if you were doing it exhaustively would scale as 2 to the 3L. So for 60 qubits, that corresponds to some 18 exabytes. You're not going to do that. And so you have to find different ways to simulate these quantum circuits. And the reason you want to simulate is to be able to benchmark your actual quantum computer when you get up to this level. And that we're able to do up to 60 qubits. The number that we factored was this one here, and it corresponded to a 20-bit number. Okay, so where are we at in terms of quantum computing and applications? There are a range of applications that people are looking at, and there are lots of tools that you can use now to study that. The approach is actually relatively old. I mean, this is something I did back in 2000, which was to adapt quantum search to bioinformatics. So there's a small class of quantum algorithms, but we can adapt them in many ways to problems that we want to solve. The key question, though, is in the era of noisy intermediate scale quantum devices, what can we actually do? And this is a useful diagram that was developed by Preskill, and he coined this whole NISQ concept. The key question is, can we eke quantum advantage in the NISQ era? And I just want to correct a way of thinking here. I know that we talk about quantum search and how effective that can be. It's actually quite hard to load data into a quantum computer in a superposition. So when you think of applications, don't think of big data, think of big models. Models that can be described by a relatively small number of parameters, such as optimization problems. But when you convert to a spin glass form and then program a quantum computer, generate a huge number of possibilities internally that you're searching over. That's the sort of application that quantum computers in the near term are possibly going to be very good at. There are lots of example areas that people have been looking at, and people can ask me about this in one of the chat rooms. In scaling up, here's an example of a 53-qubit device. This is the Rochester device that we have access to. It's not just about the number of qubits. It's all about the logic gate errors and the connectivity of the qubits. And so really what's important in scaling up and answering that question of when you would get quantum advantage is a combination of all three of these factors, which are combined in this measure that is coined quantum volume. And it's early days, but the IBM systems are currently tracking it, increasing that by a factor of 2 every year. And the question is, when we start getting more and more qubits and higher quantum volume, will we see quantum advantage? Is it imminent or within the next 5 years? I believe it'll happen. I think the Google supremacy result shows that. This is another slide summarizing the importance of HPC. And these are calculations where we simulate quantum devices and indeed these sort of random circuits but adding errors in and finding where the simulatability breaks down for a classical device. And so we're seeing that the scaling of simulation is okay with the number of qubits when the error is greater than 0.4 for this particular case, 0.4%, and becomes much, much more difficult to simulate in the no error case, and there's a crossover there. And that's very close to where the hardware is at. I believe the Google device was less than 1% error across the whole device. Okay, so just to answer the question, this is really my last slide of why quantum. Clearly, hardware development is really accelerating now. And, you know, we're at 50 qubits, and that's going to certainly increase. The quantum volume is the important thing, but that will certainly increase as well. And it could be that within the next 5 years, we have systems that have 100 qubits and very good error rates. And I think that's what you need to really see quantum advantage. And so because that's really on the horizon, there's a global push now to develop applications to unlock that advantage. And so there's been a huge amount of activity, not just amongst physicists, but many other areas in computer science, finance, AI, to really develop those applications, to learn the basic rules of quantum information processing without any of the physics. I haven't really talked about any physics here, and start looking at programming and using real computers. It's a specialized area, not just in terms of software, but in terms of hardware expertise. And so that's where simulation is important, and also emulation is important. So there's a real role for HPC in all of this. And I think that we're really at the time in Australia that we have to think about a coordinated effort in this. Clearly, we have access to these very large real quantum devices, but also there's a huge role to play for HPC in all of this. And I'll stop there.
Okay, so great. Thanks a lot. Thanks a lot to Professor Hollenberg for the presentation. We're going to have a conversation later on during the panel discussion, but there are quite a few interesting points that I think were made during this presentation. I did like, in particular, the big data to big models topic, right? So I did try myself to use the IBM quantum computer to the Bluemix cloud. I did try to use myself also various SDKs. Microsoft has one as well. Problem is, you get to a point where you kind of have an understanding of what you might be able to do, but then how do you encode the data in a format suitable, right, for consumption from these things? So I would imagine that that's probably an area of research. So that's very important to have conversation about. And the other thing is the level of abstraction to use to access these systems, because I do have myself a background in both electronic engineering and computer science, right? And I must say that I feel a lot more comfortable with seeing circuits, not code, for these specific problems, right? So I do like a lot that visualization with that UI module, right, where you see the lines, right, the parallel lines with how the qubits get transformed, right, over the. And so I'm just saying, again, another area where I believe some research will have to, be done, because today you can download a Python SDK and do quantum computing, right? But that really means nothing. I mean, you're not really doing quantum computing there. So look, we'll see. We'll discuss that probably during the panel.
Yeah, very good points.
Conversation now. I think we do have a break. We have a 5-minute break, I was told. And so while you're on the break, please do look at the screen in order to participate to our poll. It should be a one-word poll, I'm told. So we'll see what that means, but that's good. Thank you very much. Okay, I think we are ready to start. I'm just looking at the results of the polls. The poll we did, very interesting. We'll comment that later. So let me just introduce our panel members. So we have already introduced our presenters. but now I'm going to introduce the other members of the panel. One is Marcus Doherty, co-founder of Quantum Brilliance. So Marcus is a scientist, educator, entrepreneur, and I didn't know this until very recently, a soldier as well. So as a scientist, he leads the Diamond Quantum Science and Technology Laboratory at the Australian National University. And he is internationally recognized as a pioneer of diamond quantum technologies and the leading expert in semiconductor defect physics. The other panel member is Maciej Cytowski from Pawsey. Maciej is a mathematician and computational scientist and does have expertise in optimization and development of applications on massively parallel and accelerated HPC systems. And before I mentioned that somebody wanted to parallelize quantum codes, that's actually Maciej. That's the person with whom I had a discussion about this one topic. So, so that you know. So now, panel, I think we already have a few questions here. Let me have a look. Yeah, so we do have a question from the audience. The question,
Ugo, if you want, I can help you with the questions.
You maybe Aditi, you should be probably asking the question. So that's then okay, good, thank you.
Yeah, I'll help you with the questions, and then you can kind of go through with the speakers. So the first one that we have from the audience is Lloyd touched on why supercomputers are needed to simulate quantum computing. Can we talk about this further, as well as how big those systems need to be?
So I guess it depends on what you want to do. So for us, it's all about benchmarking and verification. So I can imagine a time where you're programming a quantum computer to do a specific task, and you want to verify that the results of the quantum computer are actually correct. So supercomputing really comes into play there, as we have found in our systems where we're starting to go up in the number of qubits that we use. We do find that it's very useful to be able to simulate the quantum circuit, verify that the quantum computer is actually working, or benchmark against what it should be given, and whether or not errors have actually spoiled those results. So that's a level of simulation based on the quantum circuit itself. Underneath that would be emulation, where you're really thinking about a physical device running your quantum algorithm. And that's where you may want to start injecting some realistic physics into the simulation, so that a CNOT gate, a logical gate, is actually a series of pulses. And you can vary those pulses. They might be affected by particular types of decoherence. There might be crosstalk in the device and so forth. And it's very useful to understand all that. And indeed, when we apply such characterization techniques to the IBM Q devices, we find that there's a lot of computational work to do to not only process a huge number of measurements that's required to characterize such noise in these devices, but also then to improve the control of those devices.
If I may just add a comment from a slightly different perspective. Quantum, in the development of quantum algorithms, you want to design a unitary operation which will map your input to a desirable output. If you are not careful enough, you get a billion different answers and you only be able to measure one. So to be able to do that, that's the first part of the quantum algorithm design. Once you have that unitary, you need to decompose it into a sequence of simpler operators. Those operators can be physically implemented. So, for example, you can't really design an operation which will control 53 qubits all at the same time. So you have to basically decompose it into single qubit and 2 qubits operation. And that decomposition is almost infinite possibilities. So which one would provide the optimum shortest circuit depth, and also depending on your physical hardware, there's certain operations are not desirable as other operations. So all these things needs to be simulated classically to work it out. It's a classical optimization procedure to try to find the best possible quantum operation. So in that you need a supercomputer to be able to manipulate the states in that ultra high Hilbert space.
I would also add some comments about the Google supremacy that was already mentioned, and kind of the battle between IBM and Google at that time. So the Summit system that was actually used to, at the end of the day, it was a big data challenge to solve for them, because they have used the file system, which is quite big because it has 250 petabytes to store to the power of 53 amplitudes. So basically, do a more classical algorithm on the data there to reach or try to reach the performance that was presented by Google. If only Google would use 1 or 2 qubits more for their simulation, they wouldn't be able to present that level of compute. So that the level that was already mentioned, it was 3 minutes versus 2.5 days, more or less. But Google, in their experiment, they also used their biggest system at the time to do, let's say, kind of a post-processing of the work that was done on the system, on the quantum computer.
That's an interesting point, Maciej. So, and it speaks to what Lloyd was saying about the definition of quantum supremacy versus quantum advantage, right? And that there's a subtlety there in what Lloyd said. It's about an application where you gain a performance in a useful task over a classical computer. But there's a further distinction that can be made, which is that it's a performance over a classical device in a useful task, but a classical device of the same size, weight, and power. Because in a practical engineering sense, that's what really counts to people, is does this quantum computer, which is this big, draws this amount of power, does that outperform a classical computer of the same size, weight, and power? Because at that point, the quantum computer becomes a relevant piece of technology that people will want to utilize in what they're doing.
I don't know a lot about the engineering in that paper, but I can imagine that running a quantum computer for 200 seconds, it's a fairly small device. It's a dilution fridge compared to, you know, one of these supercomputers is a pretty big disparity. That's an interesting comparison when you think of it in that way. There is another point of contact with supercomputing that I can see coming up on the horizon, and that's the way that quantum advantage is probably going to be achieved in these near-term systems is through a hybrid approach. And by that I mean the quantum computer is initialized in a quantum state that's parameterized by a certain number of external parameters that you input. And then you run the calculation. It could be an optimization calculation. You run the calculation, you look at the output from the quantum computer, and you decide where to next move in that external parameter space. And so that calculation, where you actually go to the next point in parameter space, is a classical calculation. And so there's going to be a lot of these hybrid applications, not just in optimization. I mean, machine learning is a generalization of that. And so I can see that the connection between quantum computing and HPC at a very deep level in terms of connecting the hardware is going to be more and more important.
Yeah, I agree, Lloyd. I think the future for quantum is very much co-processing, just as we've seen with CPUs and GPUs, where a tremendous change in capability happened once CPUs and GPUs were able to co-process, where you're able to distribute tasks across a hybrid network of computers. And I think the same will be for quantum computers. So when we develop the tools and the ways of thinking about how to do co-processing and to squeeze what quantum computers can do best inside a larger classical computing system and algorithm, I think that's where we'll get the greatest advantage. And this also speaks to what Ugo has mentioned about parallelism, that it also touches on that topic, the idea of being able to distribute tasks across various types of computing, quantum, classical, GPUs is another version of classical, and understanding the strengths and weaknesses and where they all fit together.
Yeah, that's also a good moment for me to defend myself. When I was talking with Ugo about quantum parallel computing, I was thinking about exactly the thing that Marcus just mentioned. So treating a quantum unit as a QPU or something like that can be treated like a GPU in your computation, like we usually use GPUs in our computation currently. Of course, with a totally different way of defining the algorithms on that device, but then having a classical computer to steer the main simulation, I would say.
Yeah, I strongly agree. I think this hybrid approach has really a distinct advantage where the quantum computer can explore this ultra high dimensional Hilbert space. So high, there won't be any classical conventional computer can even look at just a small portion of that. However, as both Lloyd and I were talking about, the quantum computer, the real disadvantage is the quantum computer itself knows everything. It has all the solutions, all the answers inside it, but you cannot, as a person, you cannot measure and look. So what is required is to design a proper way to project that high dimensional, super high dimensional space data back into the classical world. And then we manipulate that projected small space, use supercomputers, which is still large, and then feedback into this the quantum computer and search it again. So that iterative approach possibly will be very useful for near-term noisy quantum computer. I think one of the reasons for the Google computer not go beyond 200 seconds is decoherence. You just, you started the machine, you just have to stop quickly, otherwise things decohere and you lose all the information. So then, but it can explore very huge space and let it do the best they can. Shorter time, large space, projected back to the classical world, and the classical computer can do much longer. And then, and then go on. That's from me. Yeah, I do agree with everything others are saying.
Okay, thanks a lot. Sorry to interrupt, but conscious of time, we do have a few questions that are coming in, right? I believe Aditi might want to ask another one, which I think we just got. So.
Yep. So we just got another question from the audience. It's possibly a multifaceted one. A programming language compiler for a classical computer generates machine code for a concrete target machine. What's the analog for a compiler targeting a quantum computer? We're now seeing tools for hardware synthesis from C or C++ instead of hardware description languages like Verilog or VHDL. Is compilation for a quantum computer more akin to hardware synthesis from a programming language to a field programmable gate array, FPGA, or an FPGA emulator than to a classical computer's machine language?
I can probably have a go at this, and unless somebody else wants to jump in, but I actually showed an example. It's multifaceted, multi-layered. I showed an example where we went from the circuit diagram for Grover's algorithm to the compiled circuit that's actually run on the machine. So that's kind of like a first level assembly language. that it compiles to. But within each of those boxes, there's a series of commands which are literally pulses that are sent to various parts of the device operating on qubits and their interacting components that are basically written out automatically and optimized. And IBM allows you to have control at that level as well. It's called Open Pulse. So you can start to look at designing and optimizing those pulses as well. So compiling in a quantum computer involves a lot of layers that can go from just looking at the logical level and trying to, if you've got certain logic gates next to each other, they can be collapsed in one slightly different one. So you save on time steps, all the way down to optimizing the actual pulse control of your quantum computer. The overall aim at the moment is to shorten the number of time steps because, as was mentioned, these devices are not error corrected in a quantum sense. So the number of time steps before you get an enscrambling of results due to errors is very limiting. So you have to compress the circuit as much as possible. And that is the primary task of any compiler at any of those levels.
If I may add, just very quickly, this is a long time ago now, 2013, we published a paper which we call it a Q compiler. And this is a quantum compilation with some mathematical methods. So essentially, if we are giving a quantum algorithm we need to implement, we can compile it to decompose what is required to do into a sequence of physically implementable gates. I'll stop here. Yeah. So that's really down to the assembly level. And really addressing, as I mentioned earlier, you can't control 50 qubits all at the same time. Well, all you can do is 1 or 2, or maybe 3. So the compilation requires you to decompose that big unitary operation into lots of them. Each one implements 1 or 2 qubits control. Thanks.
So Jingbo, I think, correct me if I'm wrong, but what you're talking about is a higher level of compilation to what Lloyd was talking about. So you were saying that you have a desired unitary, which you then compile into a string of command operations. Lloyd was then saying you receive a string of operations, you then compile them into a set of operations which are realizable on that particular machine. And then from that particular set of instructions, then compile them into the physical commands and operations which are performed on the computer. So was that right, Jingbo? That was a higher level of compilation.
Yes, I agree. Yes.
There's another interaction that's worth talking about that, again, links to the classical computing space. And that is when you do want to load data into your quantum computer. So in our student labs, we just last week had them doing a quantum finance problem, which was a option pricing problem. And there you need to analyze a particular distribution of data. And so it's to be able to load data in a quantum computer at the moment means that you have a small quantum circuit which you optimize externally through a classical optimization program, and it could be machine learning, to generate, basically change those elements in the quantum circuit so that what's generated as a quantum state is basically a distribution of amplitudes that follow the data distribution that you're trying to load. So that's as you get more and more qubits and a finer grain distribution that you want to load in your quantum computer, that becomes an ever bigger task to do. So I think there's going to be a big role for classical computing in that particular task as well.
Okay, thank you. Actually, I did have kind of a follow-up question to this very question, right? So you were talking about compilation, right? But is it the right term? Because look, I was designing myself, electronic circuits, right, at the time, and I was using a software called ViewLogic on a Spark station in the 90s, right? And there we would design the circuits, generate VHDL, and that thing would then result in either an FPGA type of circuit burnt into the logic, into the FPGA hardware, or sent to manufacturing, right? There was no compilation at all there. So the question is here, what does it mean to really compile something for a quantum computer? What is the product that you need to give to a quantum computer to then implement those circuits we saw there? What is that? Because on CPUs, it's machine code, right? It's just machine code. It's a file with binary codes and instructions. What are you giving to a quantum computer? What is it, the product that needs to be given to a quantum computer?
So I might. Oh, Lloyd, did you want to go first, and I'll jump in? Or?
Yeah, because I tend to forget what I'm going to say. Right, I'm getting to that age. Well, it's nearly happened. I've nearly DK here. So first of all, the word compilation is something that probably physicists bandy around too much without thinking of it. And we think of translating text that we type in as a program, and somehow it's compiled into something that the computer can recognize at a hardware level. That's probably how we think of compilation. And I believe the nomenclature is changing on this in the quantum computing space, and it's often referred to transpilation. So in other words, transforming a circuit that you might write directly from quantum mechanics mathematics into a series of commands that can be run on the actual hardware. That's at a very high level view. If you're a high school student using the quantum experience, then what it means is translating the sort of circuit that I showed you into a different circuit that represents the operations that are more natural for a quantum computer to run. That's what compilation means. If you're a physicist, then compilation means I'm going to program certain logic gates in my quantum circuit, but I know that what's actually being done is a certain sequence of pulses of a certain shape are being implemented on a microwave bus or on the superconducting qubits directly in order to affect the physical processes that represent those logic elements in my circuit. So it's not a great terminology for quantum technology, I think. And I think we probably need to be a bit more specific in that language. But we're at very early days in all of this. For some people, compilation is going to be, I'm working on my C code and I've got a particular function that I want to implement, and I'm going to put a Q in front of it. Not like the old Fortran days for double precision, but it's actually Q for, say, a Q search of a database. For some people, that represents something that's then going to be compiled, and I don't care. It's going to do something quantum. At this early stage, I think it's all about understanding what that process is in order to get the most out of your technology.
So what are the most promising areas to pursue with quantum computing, and what opportunities to develop applications?
Well, I'm happy to jump in, but I don't want to always do that. So it's hard to say what's the most promising because as I've always maintained for the 20 years that I've been in quantum computing, that quantum mechanics always surprises. So there are always things around the corner that we just never thought were going to be possible. And Shor's algorithm is actually one of those. Prior to Shor's algorithm, the best quantum algorithms, as it were basically two classical steps was condensed into a single quantum step, for instance, and that was the speed up. That was the so-called Deutsch-Jozsa problem. Quantum error correction was another surprise. So around the corner, we don't know really what's going to happen, but from what I can see in the way things are tracking, the variation quantum approaches to material problems are showing promise. Optimization, we can see our way through how to use the so-called quantum approximate optimization algorithm, which is one of these hybrid classical quantum approaches to a whole range of optimization problems. the various ways that quantum interacts with AI, both in terms of doing AI on the quantum computer and using AI for the quantum computer, is also another promising area. I wouldn't want to tie myself or nail my colours to one particular mast in this sense. I think there are a lot of promising areas and more are being discovered all the time. The big thing is going to be when one of these areas can demonstrate quantum advantage. And I think it's around the corner, but I wouldn't really want to say which area that's going to be.
I think there. Oh, sorry.
You go for it, Maciej.
Okay.
So I was just going to say that there's also more to delivering quantum advantage and where it can be found. So there is the algorithm discovery and identifying algorithms that scale well and provide an advantage in terms of scaling resources. But there's also then the other side of it, which is the full workflow of solving a problem. So we've already touched on various points. So that is, how is data distributed to the quantum computer? How is input and output managed? How is that then reconciled with another classical computing system that will be doing work in parallel? So that whole workflow use case validation is so critical to delivering quantum advantage in the near term. So there's algorithms which might say, yes, with scaling, we can deliver quantum advantage, but then when it comes to the actual workflow and implementation, it can't deliver that advantage due to hiccups and problems. So there's two sides of the coin. There's algorithm development, and there's also the systems design, the workflow design around quantum computation. Maciej.
Yes, there were a couple of other things mentioned in Professor Wang's presentation as well. I think quantum chemistry is something that is also a field of interest in terms of applications. In the example that we have been referring to a couple of times, so the Google quantum advantage, that was a big question of usefulness of the algorithm that actually was run on the system. But I think current research is going towards using that particular algorithm in some kind of cryptocurrency applications. That's another field that might be seen as an interesting area.
Quantum computers will give the correct result with high probability. Do we know the probability distribution over all the solutions? And do we know, or can we compute the probability of every solution? Also, is the probability proportional to the quality of the solution?
Well, from using these systems, one of the things you find out immediately is that you don't run the calculation once, because you just get a random result out, which is guided in principle by the probability distribution. But because of errors in the device, that probability distribution might not be exactly as good as what you predict theoretically. So you tend to run these calculations perhaps 1,000 times, and you can then build up that probability distribution and pick out, in the case of optimization, what might be the highest probability results are actually the ones that correspond to your solutions. Now, as your circuit gets longer, those probabilities get more and more scrambled. So you saw in the case of the quantum search on that 5-qubit device, already you started to see the probability distribution change, and the probability of the marked state come down and the unmarked states go up. So when you have many more qubits, that distribution is much more complicated. There's more scrambling that happens. And so a lot of research now has gone into not just compression of circuits, but how you mitigate errors that occur in the final distribution. And funny enough, one of the most promising ways of finding out how to mitigate errors is to introduce more errors by putting in more gates that effectively do nothing but extend your circuit depth. So you get another point that corresponds to a high level of error, and then you reduce that level of error and extrapolate down through the best to the ideal. And that tends to actually work. which is quite amazing.
May I add to that? If you do the quantum computing on the basis of 2 to the power of n possibilities, and then that's going to be a huge, astronomically large number. So that's the main reason for us doing quantum computing, not classical computing. So it's not possible to sample 2 to the power of n, and nothing close to that. So what you can sample will be log 2 to the power of n. And if you do that, it's not going to give you any probability distribution. You're just going to get a random numbers, possibly one at a particular, for a particular value. So what I'm saying is, you have to start to really think hard how you design the quantum algorithm so that it's not going to be really rely on this distribution, because this distribution will only be known by the quantum computer. We won't be able to. We just can't sample. There is not going to be a distribution to be sampled because the basis is too large. So the design is, you have to design it. You don't know where it is, but you have to design your algorithm. So when you measure, the best possible solutions will have high probability. Yeah, that's just what I want to add. Yeah, so when you read about quantum sampling, be very careful. You just can't sample to get a distribution.
Okay, so the last question is, can the team provide a view on the status of progress at IBM, Google, Rigetti, etc.? Is one organization winning, or can they all achieve a degree of mutual success? And can the small team compete with those companies with the large balance sheets?
So I might chime in first, if I can. So I think we're in an era at the moment where it is about discovery of applications and discovery of what types of quantum computing architectures give advantage for particular domains of quantum computation. So I actually think the era at the moment is about diversity. It's about being able to engage with a variety of platforms which are sufficiently sophisticated so that you can explore different architectures and how those different architectures give rise to different advantages. So Lloyd mentioned about the idea of quantum volume and how that's a representative of 3 different factors. One of them is around the network of qubits and the connectivity of those qubits. Another is around errors associated with different connections. Different architectures give rise to different networks and different errors. And some will be good for certain sorts of problems which rely on certain gate operations, and others will be good for other different types of problems. So at the moment, I think it's core to pursuing and advancing quantum computation is diversity and comprehending that diversity. So it's not about winning or losing at the moment. It's about discovering what makes quantum computing work best. And in that situation, small players are important and do deliver value to people.
I'd also add that it depends what your context is. I mean, I thankfully don't have to buy into this competition between the majors, right? They're all doing slightly different things. And I think what we define as the forefront in a particular direction is going to be matched by perhaps another physical platform. They'll be very different. We're all learning how to program quantum systems that have emerged actually quite rapidly beyond the 2 or 3 qubit to the tens of qubits. And as Marcus says, it's all about optimizing how you perform quantum information tasks on each of those devices. And we talk about quantum advantage and how it might be, you know, around the corner and so forth, but it is in this NISQ era where things are pretty much still a little bit noisy, not really error corrected, or if they are, it's in a very rudimentary way. When we talk about a full-scale quantum computer to actually run Shor's algorithm for relevant bit sizes, like 2048 or something like that, we're really talking about massive redundancy that has to be built in for quantum error correction. And that's when you get into the many thousands, if not millions of qubits in order to run fault tolerantly. So we're a long way from that. So we're at the very beginning. How can small groups become involved when the majors are spending billions? Well, thankfully, they're actually providing online services and access to their machines. And I think now is the time that, we have to take advantage of that. And that's why I've been part of establishing the Q Hub at Melbourne, is to have a mechanism for people to get access to these systems, because we're not going to be able to afford to build a 53 qubit superconducting device. But if they're put out there for access, I think that's very important for smaller scale groups. And I don't just mean physicists, I mean quantum scientists, computer scientists, software engineers, finance people, people in a whole range of end user areas are able now to access these devices, even though they're incredibly complicated and very sophisticated. So is the programming interface and the whole software stack associated with that. So I think we're in a rapidly evolving situation now. And I can see, that's why I put in my last slide, that I can really see that there's a need in Australia now. We've got a huge amount of fundamental quantum expertise, but I think now it's time for a coordinated effort to bring together not just that level of expertise, but also people in computer science and all these other areas that would like to use that technology, and to have these groups of people work together on these different systems. And I think there's a huge role for the Pawsey Supercomputing Centre and NCI to actually work together on this.
Good. Okay, so I think this event is coming to an end. It's almost 4 o'clock. It's been great talking to all of you. I think we could have gone, on for another couple of hours at least, but that's the time we have allocated to the event. But I think it was mentioned already in the comment side, I think in the chat, that we will have another event that we're organizing at the end of August. And then if this thing gains traction, right, we can even resort to having regular events about quantum. We don't know yet, right? We will see what happens. Even a special interest group, whatever makes sense to do, right? We'll see what happens. So let me thank again everybody for joining our meeting today, and please do check the program for our Pawsey Fridays. We have that on our website. I do not know what and when the next one will be. Maybe Aditi might be saying something there or not.
They're listed on our website. So if you go to pawsey.org.au/events, there's one at the basically the last Friday of July, the last Friday of June, June, July, and August are now organized. The quantum event in August is still to be listed on our website. So I recommend you sign up to be a Pawsey friend, and we'll get you registered and send you more information when those events are confirmed.
Okay, great. Thank you very much, Aditi. And also let me thank Aditi and Karina for organizing this, because to be honest with you, until yesterday, we didn't know how this thing would work, right? We never had organized anything this big before. So, it went pretty well, I would say. So thanks a lot for organizing it. And thanks again to our speakers and everybody who joined today. Thank you very much.